Welcome to the SPSS Statistics Frequently Asked Questions series, and in this section we're going to be looking at how we can use SPSS Statistics to check for normality. Now if you're interested in checking for normality, chances are you probably have some understanding of what the normal distribution is, and the fact that there are thousands of examples of natural phenomena that appear to be normally distributed, whether it be temperature, height, weight, strength, or test scores or intelligence. You'll also be aware that the normal distribution has some fairly nice, easy to identify properties, which is simply that it's symmetrical, it tends to be bell-shaped, sometimes called the bell curve, and that measures such as the mean, the median, and mode all occur right at the same position, right in the center of the distribution itself. You may also be aware that normal distributions can be divided up into the same proportions by the standard deviation, so that, for example, 95% of the area on the normal curve lies within roughly plus or minus 2 standard deviations of the mean. So the normal distribution is quite important within statistics, and although there are many more examples of phenomena that do not seem to be normally distributed, one critically important thing often seems to follow the bell-shaped curve, and that is error or measurement error. And for that reason, a lot of classic parametrical statistical tests assume that the data follow a normal distribution. So let's have a look at the steps we can take and the procedures we can run within SPSS Statistics that can help us assess whether or not a distribution in question is in fact normally distributed in the population. Okay, so here we are in SPSS Statistics, and it's SPSS Statistics version 25, and we've got 3 different columns of data that we're interested in here, distribution A through the distribution C. They're numerical or scale or continuous variables, and there are various techniques that we could employ to assess the degree to which we regard them as normally distributed. We could, for example, do some visualization, some histograms. We could look at the descriptive statistics and see whether or not for each distribution, whether or not their respective means and medians lie within the lie close to one another. We could see how symmetrical the distribution is. We could ask for measures such as skewness that tell us whether it's skewed positively or negatively, and so on and so on. And there are even some statistical tests we can run. It turns out that there is a place within SPSS Statistics where we can pretty much do all of this within one location, and that's the Explore command under the Analyze Descriptive Statistics menu here. So if I click Explore, and if I pick on, say, distribution A to begin with here, that's my continuous distribution, my target distribution I'm going to assess. I put that into the dependent list. And what I normally do is I normally switch off or change some of the default settings. So if I click here on plots, I usually switch off stem and leaf plot and ask instead for a histogram. And I can also ask for normality plots with tests. So if I click continue at that point and click OK, it goes and pushes the results out for me onto the output screen. We can see there's a lot of different values and statistics here. Let's just jump down to the distribution itself as shown as a histogram, which we requested there. This is obviously very powerful because histogram's an instant way for us to assess a distribution, because we know what a normal distribution should look like, and we're asking ourselves, well, is this a symmetrical bell-shaped curve? Well, it looks like it's not terribly symmetrical. It definitely looks like it's skewed somewhat towards the positive end. It's not especially bell-shaped. Would we say that that is normally distributed enough for us to regard it as normal distribution? Well, if we look at some other plots that we have here, we have something called a normal QQ plot. Here we have the observed value and we have the expected normal value. If you're wondering where it's getting that from, well, if you go to the chart editor here and open this up, you can usually ask for a normal distribution curve to be added over the top of that, and you can see there's a normal distribution curve shown over the top of that distribution. And of course, the way in which it's putting that curve there is simply looking for the mean and the median to find the center of it, and then it's stretching the curve out in such a way that it encompasses the requisite number of cases as per the properties of the normal distribution and the standard deviation. So it stretches it out so that one standard deviation above and below the mean accounts for 68% of the cases, and roughly 2 accounts for 95% of the cases. So it can compare the actual distribution to the normal distribution. So that's one thing, that's one clue here. We can see that a lot of these cases fall outside of that bell-shaped curve. And this is really just showing where they fall outside that curve. So this is saying that, you know, if it was truly normally distributed, we'd expect all of the dots, all of these cases to fall exactly on that curve. And as we can see here, that as we get to the extremes, they're not really falling in the curve. The detrended and normal QQ is a similar sort of thing here. We're not so much interested in whether or not things lie within the curve, but rather whether or not the points are randomly distributed around the curve, in which case we might see a sort of zigzag pattern if it was just random. But here we're seeing a distinctive U-shaped pattern, which is associated strongly with skewed distributions. And finally, we even have a box plot here where the box shows the middle 50% of the data, and the whiskers above and below the whiskers, the bottom 25% and the top 25%, except for those cases that are deemed to be outliers, and outliers indicating, of course, that they are positively skewed. They're quite high above the 75th percentile, and therefore the plotted outside, because they are more than 1.5 times the interquartile range above the 75th percentile. But the point is that they're regarded as outliers, and that makes sense because we're getting a kind of positive skew here. And then if we go back up to the descriptive statistics, we can see the mean value here is 234. It tells us 95% confidence intervals of that. It tells us what the trimmed mean would be if we chopped off the top and bottom 5%. You can see here that the top and bottom, 2.5%, 5% trimmed. It brings it down to 229. The median's 219. So we got some skewed values here, hence we get a positive skew value here. And then we get tests of normality. So we get some statistical tests. And what we find is here at distribution A that we have something called the Kolmogorov-Smirnov test, and it's got a Lilliefors significance correction. So it's sometimes called KS Lilliefors, actually. And it's showing a statistically significant result. And the null hypothesis that is being tested here is really that in the population, this distribution A is in fact normally distributed. And the reason it doesn't appear normally distributed for us is simply due to sampling error. Simply if we were to sample it again, it would probably change. If we sampled it again and again, we might get some distributions which were normally distributed and some which weren't. But here it's saying that the probability that the distribution is in fact normally distributed in the population is very small, and therefore we reject the null hypothesis that this is a normally distributed phenomenon that we've got here. So in the same sense, we have another test here called the Shapiro-Wilk test, and it's doing the same thing. It's giving us a value which is less than 0.05, which of course is our standard rule of thumb for accepting or rejecting a null hypothesis. The only thing that's to bear in mind here is that the KS test here, the Kolmogorov-Smirnov test, is regarded as quite not very robust. It's quite a weak test, and that Shapiro-Wilk is regarded as a slightly stronger test, more reliable test, especially when the values are not tied. That means that when we don't have too many cases that have exactly the same value, which we might get with, say, a rating scale. Okay, let's look at the second one now. Let's do the same thing. We'll go to Explore now. Let's look at distribution B. Click OK. We'll look at distribution B. We run that, and we've got another Explore command out here. Let's look at the histogram. You can see now this histogram here looks a little bit different. If I double click on it and ask it to put a normal distribution over the top of that, it's not falling exactly on it, as we can see here, but it looks more symmetrical than before. We can also see from the QQ plot here that most of the points lie directly on the line. They pretty much all lie on the line, even around the extremes of the distribution. And the detrended QQ plot is no longer showing this shape, this U curve shape that we were getting earlier on, so it's a bit more random than before. And we can see that the outliers are kind of symmetrical here in the box plot. So this is looking much more like a normal distribution. When we look at the descriptive statistics, the mean is 149, the median's only 148, so they're very close together. The skewness value is very small, it's not very big at all. And the KS Lilliefors test here is telling us that the probability that it is in fact normally distributed in the population is about 0.2. Here it's much stronger, Shapiro-Wilk at 0.69, so some difference here between the tests, but in both cases we accept the null hypothesis that this is a normally distributed phenomenon that we got here that we're assessing. Okay, let's look at the third one. This is distribution C. I click OK, run that again. Again, let's go down to the plot here. Now again, the plot here looks fairly normally distributed. Is it normally distributed? Is it normally distributed enough? Well, if we look at that, you can see that this curve here falls very, very close to that. Is that a normally distributed distribution? We can also see that the QQ plot very, very tightly distributed on C, value C. And is this random? It's looking fairly random. The box plot again, very symmetrical. This is looking very strongly like a normal distribution. If we look at the mean value is 33.9, the median's 34, just barely more. And what's interesting is when we look at the test of normality, this is when we get a difference of opinion between KS, Lilliefors, Kolmogorov, Smirnov, and Shapiro-Wilk. Whereas Kolmogorov-Smirnov is telling us to reject the null hypothesis that the distributions are in fact, that the distribution is in fact a normal distribution in the population. The Shapiro-Wilk's asking us to do the opposite of that. It's saying that it's not less than 0.05. It's actually a value of 0.09, so you should accept the null hypothesis. And as I said earlier on, Shapiro-Wilk is regarded as a more robust statistical test, so I think we'd be fairly safe in this situation of accepting normality or assuming normality in this distribution. Of course, the question of what we do with data that we detect or assume is not normally distributed based upon our exploration of it, well, that opens up a lot of different possibilities for us. We might do some transformation of the data to force it into a normally distributed phenomenon, or we might go down a different path of testing. We might go down the line of running non-parametric as opposed to parametric tests. But that is a topic for another FAQ.